So, we were talking last time about free surface flows. I think we tried to make the case that free surface flows weren't really very different from pipe flow or external flows. They all really conform to Bernoulli's expression, where we have an extra term that includes head losses. The difference for free surface flows is that they are able to they have an extra degree of freedom, if you like. So rather than being constrained to the cross-sectional area of a pipe or being constrained by the flows around them, the surface of the flow can choose its own elevation. And so in doing that, you get these vagaries of different flows. And so you see on the left-hand side of this a nice smooth wave coming in that changes into this turbulent wave. Of course, that's probably not because it's on a smooth bed. But we did talk about classifications last time, where we divide things into what we call uniform flows, which is really what we spent our time talking about last time. Gradually varying flows, where we could imagine that it would change from a shallow, fast-flowing flow to a deeper, much slower flow, same volume rate going through, and also rapidly varying flows, and so which we didn't talk about. We talked about the first one only. And so surfing West Virginia is really part of that picture. You get these changes in behavior going on, and you can do interesting acrobatics. Of course, most of this behavior is kind of a balance between when you're surfing waves like this, you have the wave going underneath you with viscous drag on the boat, and if you're on the front side of a wave, then you have gravity pushing down on you. So you have a force pushing you up, ostensibly up the surface of this wave, and you have gravity pushing you down, and that's why you can hold yourself in one place on a wave in a river, which really isn't all that different from waves in the ocean. So we talked about that. I don't know, hopefully it's muted, so this. And we also talked about this hydraulic jump. I don't know whether I found this one. This is the one I wanted to show you, which really does show this change in behavior as you go from left, where you have shallow flow, to right, where you have this different flow. Not different in many respects from, you could imagine these waves that we saw on the, I don't know if it's the New River, one of the West Virginia rivers. And by continuity requirements, we know that for continuity of flow, the flow rate, if you cut it on the left-hand side or if you cut it on the right-hand side, have to be equivalent. And so from what we know about the cross-section area of flows, we know that the left-hand side has to be flowing faster than the right-hand side. And so that's kind of where we left it last time. We talked only last time, let's see if I can pull my stuff up. Oh yeah, I do. So I do have it here. So this is kind of what we talked about. This is how we made our connection. Let me do this, so it's full page. And so these are the kinds of behaviors that we're talking about. What we talked about last time was stuff that inhabits this area here, these so-called uniform flows. And so that is that the depth doesn't change as we go downstream. And so we talked about that last time, and we came up with these expressions which define behavior for this particular condition here that we explained at some length. And this condition here is one where the bed of the flow, which slopes at some gradient S0, is parallel to the depth of flow. In other words, the depth of flow y doesn't change as you go downstream, so-called this dy dx equals 0, this condition here. And if that's the case, we made the case also that the velocities have to be the same as well because of the cross-sectional areas, by definition. And that's kind of our routine pipe flow equivalent example that gives us these expressions which say that the velocity of flow we can calculate if we know the depth of flow, which is recorded in this hydraulic radius. Hydraulic radius is equal to just the area over the perimeter of flow. Some coefficient that describes the the roughness, if you like, or the viscous loss or the frictional loss within the system, which is this Manning coefficient n, which we can get for any kinds of channels that you could imagine for different materials. For different materials that are rougher, it'll be larger, and so it'll have a larger resistance in the cases where it's rougher. And as a function of the inclination of the bed. So the inclination of the bed of the channel you'd know. If you know the cross-sectional area of the channel, you'd also know the hydraulic radius. If you know what the channel is made of, you know the Manning coefficient. And the only unknown in some respects is that you don't necessarily know the depth. You'd have to prescribe the depth in some way. And if you do know the depth, because the depth obviously is part of this expression, so we drew this idealized channel last time, that the perimeter is going to be this magnitude here, and the cross-sectional area of flow is going to be the cross-section. And we could divide it up in some way to be able to do that. And we talked about ways of doing that, and what you should use as the perimeter, and what the most efficient cross-sections would be for flow within these systems. And so I think there's enough stuff online, and you'll do some examples for your homeworks that you'll work out exactly how to do that. It's just formulaic, and so it's not perhaps what we should spend most of our time doing. So this is what we've spent our time working on last time. Flow classifications, uniform flow, gradually varying flow, rapidly varying flow. We talked about one of them, which are these uniform flows, UFs. And we have the Manning and Chassis formulae that allow us to calculate flow rates for that. So that's kind of the vanilla material, I guess, for open channel flows. The more interesting ones are when you start dealing with what we'll refer to as gradually varying flows, ones that can change in depth as you go upstream or downstream. And so to be able to do something about that, these don't change very rapidly. So this rate of depth change with length is typically very small. And we need a couple of different concepts to be able to deal with those. It's kind of interesting that it goes hazy there. And the concepts that we need to deal with it are that now we're going to take this left-hand side behavior. We're going to admit the fact that upstream and downstream depths can be different, as given by this requirement that dy dx is not equal to 0. And as a function of this, we made the case last time that because of this velocity head term here will by definition change from the downstream location, Vd squared over 2g, relative to the upstream. And based on continuity, this velocity clearly has to be larger than this velocity just because of the cross-sectional area flow. And so now, each of the slopes of these components are potentially different from each other. There's no reason why they should be the same as each other. And so it adds an extra wrinkle, if you like, into what we are doing. Bless you. The other thing that's probably worthwhile doing is that, and we talked about it last time, is that all of this is defined absolutely in terms of Bernoulli's equation. So you can write Bernoulli's equation upstream at point 1, and you can write it downstream at point 2. And these individual components that we deal with, this is going to be what we referred to as the hydraulic head, right? Not writing very well here. Because this, by definition, is our hydraulic grade line, HGL. And that's just a fancy way of saying that the sum of elevation head plus pressure head is equal to the hydraulic head. And that's given by the grade line as it transits across our system. And in addition to this, the energy grade line is this top line here, which shows how energy changes across our system. And in this transit across our system, this amount here is what we've always referred to as H sub L. So if you write Bernoulli equation between the upstream and the downstream, then you end up with these three components. Elevation head, pressure head, velocity head is equal to downstream elevation head elevation head, pressure head, velocity head, plus cumulative losses. So it's absolutely no different from what we talked about before. Ignore this, these are my notes. And so how do we deal with these cases where we have to now look at this response as we go downstream? To be able to look at, for instance, these kayaking videos that we just looked at, to be able to describe those behaviors. So it takes an interesting twist in that we require an extra piece of information which doesn't seem particularly rational. And the piece of information that we need that doesn't seem particularly rational is that, surprisingly, for these systems, we need to know something about the wave velocity. And so in most of the systems that we've dealt with, we've classified our behavior, well, actually we can draw it here, right? The behavior that we've talked about in terms of Moody charts, etc. Just to redraw this. Reynolds number varies as a function of, we've made this case that it's friction factor, but it's really kind of an Euler number that occurs here. It's actually a reciprocal Euler number. And we have these behaviors for laminar versus turbulent. This is this RE critical. We've never really called it that. I call it RE critical because it changes, right? From this behavior that's laminar versus turbulent, it changes depending on how we define it. If we define it in terms of hydraulic radius, then this is 500. If it's in terms of hydraulic diameter, it's 2000 because the factor of 4 between them. But these are the behaviors that we get. So we've cast all of the behaviors that we've talked about so far in terms of these two dimensionless numbers. But you remember that when we talked about dimensional analysis, we also talked about another number, the Froude number. Maybe it's worthwhile writing it out, which is equal to a velocity divided by a length scale and gravity, square root. And so we could write it that way, which is how it's usually written. You know that any of these numbers we can write kind of arbitrarily, so we could square this. And if we square it, then we get a number which is just this, which is no different. But you'll notice that this v squared term is really the inertia that's in our system. And so this is the same inertial term that exists in the Euler number, if you remember. So this Froude number turns out to be an important number when we're talking about free surface flows, because it's the velocity of the surface wave which controls how information is transmitted within the system. And so we'll get to that soon enough. So you're listening to me right now. My voice comes to you courtesy of the air which is between us. If you wanted to calculate the rate at which my voice came to you, you could use the equation for the acoustic wave, which is the stiffness or the bulk modulus of the air which is between us, and the density of air. If you wanted to calculate it, you might remember that in a gas, the stiffness of a gas is equal to the pressure and the density of air. And so if you wanted to calculate what that is, you know that the pressure here is 100 kPa, so that's 10 to the 5 pascals. It's divided through by 1 kilogram. So the velocity is something of the order of square root of 10 to the 5 meters per second. So 10 to the 5 is 10 times 10 to the 4. So square root 10 times 10 to the 4 is 3 times 10 to the 2, right? So it should be something like 300 meters a second. And I think there's a factor of 2 difference between meters of seconds and miles an hour. So it's like 600 miles an hour, which is the speed of sound. And you know that commercial planes go slightly slower than that. It's about 500 miles an hour. So if we wanted to get the speed of sound in a gas, we can get it by using this, which is the same expression for solid. If you want to know how quickly sound travels as I hit the bench and it moves along there and I feel it further down, then I just use the modulus of the bench, which is a couple of GPa. Water is a couple of GPa. If you wanted to know the speed of sound in water, then we could just use, in water, it would be something like Modulus is something like 2 GPa, 2 times 10 to the 9 pascals, and divided by 1,000. And so this is kilograms per meter cubed. And so what is that? So that's 2 times 10 to the 6, which is about 1.4 times 10 to the 3. I think it's written down at the bottom of this page. So the speed of sound in water is of this order. So it's faster than it is in air, but it's slower than it is, for instance, in rocks. And so we made this analysis before. We talked about tsunamis off Japan, how you could have ocean bottom sensors 100 kilometers offshore where an earthquake occurs. You get the signals from that sent wirelessly at the speed of light. On land, it takes maybe 30 seconds for it to arrive on land, and so you have 30 seconds to get out of a building, turn off the gas, etc. And so the difference in these wave speeds is important. So those are wave speeds in full systems, but that's not what we're necessarily interested in. We talked also about the wave speed of the so-called celerity wave. Is that written here? So yeah, celerity wave. And so the wave speed of the celerity wave is much slower than the acoustic speed, either in water or in rock. And it's the rate at which a wave would propagate if you have a fault sitting on the bottom of the ocean, slips relative to itself. This offset here becomes a drop on the sea surface just because it's transmitted through the sea surface. And you get a tsunami going off in each of these directions as a result of this solitary wave. And we can calculate the rate of that. In fact, it is calculated maybe later, but we don't need to do that. Take it on trust that we can calculate the magnitude of that, and it turns out to be this magnitude here. It's equal to gravitational acceleration, so it matters what planet you're on, and it's equal to the depth of the water, which is this magnitude y. And so the Froude number is the ratio of a velocity of the water relative to the rate at which a wave would travel within that. And so that's important because it really governs how information is transmitted in surface waters. I don't mean to be jumping all over the place here. It's almost always true that this wave speed is the case. It's sometimes referred to as the shallow wave expression because it exists for shallow waters close to shore and also in channels, which are shallow compared to the wavelengths of things. And it's not necessarily completely true in deeper waters, say at the Marianas Trench or whatever the deepest parts of the ocean are, where it tends to be this behavior. You'll see this expression in your book, where we can look at the magnitude of this wave speed relative to the wavelength. So the two controlling factors are the wavelength between two crests of a wave. So you throw a stone in some water, you get ripples that go out, you look at the distance between those ripples, and that's by definition the wavelength of that wave train. And you compare that to the depth of flow, not to the height of not to the amplitude of the waves, but to the depth of the flow relative to the surface that it sits on. And so as you get longer and longer wavelengths compared to the depth, then the behavior of waves asymptote to this magnitude here, which is this equation here, which is the only one we'll use. If you look at much deeper waves where it's much deeper, and therefore for given wavelength of the wave, the ratio of those two is much smaller, in other words, at this end, which might be in the middle of the ocean, then the behavior tends to this response here, which is this expression. So it's different. But for all intents and purposes, we'll use this because it characterizes our behavior. Interesting that it has this kind of fuzzy part here. So what's the reason for wanting to know this? Well, one reason is that Froude numbers and wave speeds control how information is transmitted. So if I'm speaking to you, you hear me, hopefully you understand me, and you process that in some way. and it arrives at the velocity that I send it to. So velocity is length over time. So if you know the velocity and you know how far you are away, you can calculate how quickly it gets there. If I was moving away from you at the speed of sound, then that information would either be delayed or never get to you, right? Because of the rate at which it was emanated from you. And so the same is true in moving water, is that if you imagine dropping a pebble into a pond at this point, and you look at taking a strobe of where the crest of the wave is at any particular time. At time 1, it'll be here, time 2, time 3, time 4, times 5. And the rate at which that emanates from the center is governed by this celerity wave velocity, surface wave velocity. And so that's fine. We know that. If you imagine that water, instead of standing statically, is actually moving, then when this first disturbance exists here, and it moves out, in the time that it takes to get to the second place, the water's physically moved downstream. And so if you think about exactly what that would look like, is that you'd end up with these kind of concentric circles. They would not be centered on the single spot as they were before, but they would be offset in some way. And so if it's going less than the speed of the celerity wave, then there's still some information that's being traveled upstream from the disturbance. If you imagine it going at exactly the same speed as the celerity wave, then it would look something like this, right? You'd get the blip from the first water you put in. It's trying to go upstream at some rate, which is the velocity of flow. It's getting pushed back at exactly that same rate. And so you'd end up with, for the second time, it would be still centered at the upstream location, which is here, but it would, at each successive time, it would be these non-concentric circles, but circles which are actually have a linkage in terms of the side of the circle at this one point here, and the diameter of the circles would be equal to 2 times the radius. And you can calculate the radius if you know the velocity, right? If we know the velocity is equal to length over time, and then we know that the length is equal to the velocity times time. So you know the wave speed velocity, you know how long it was since you dropped the pebble in, so you can calculate how far it would go. And so the diameter of this, I guess, would be twice times this length for any particular time, right? Because it's twice the distance. And if, on the converse, now the stream is going faster, so the flow rate of the stream is larger, so Vs is greater than square root gy, then it would drop here, and as it expands, it just gets carried downstream and it gets larger. Again, this diameter would be 2 times this magnitude that we're talking about here. You can calculate the length at any particular time. This would be the celerity wave speed, right? This would be square root gy. And the only important thing about that is that now, if your only way to communicate with someone upstream because you're drowning is you're splashing in the water, they'll hear your voice, but they'll never hear anything. They won't hear your splashes. They won't see your splashes. And so this is kind of crucial, and this is the reason why we can get these behaviors that we talked about earlier, which come into this. What's this? I don't know what this is exactly this behavior here. And so now we have something going on that's downstream. If communication cannot occur from upstream to downstream, it's completely disconnected as to what these two things are doing. They have no information from each other to be able to communicate. And therefore we can have these two different states that exist between upstream and downstream. It's because there's no communication occurring between them. So that's an important component for us to realize. And so this Froude number is just the ratio of the flow rate of the stream versus the celerity wave velocity. When it is flowing faster than this, the Froude number is greater than 1, there's no communication. And when that happens, we call it a supercritical stream. It's flowing faster than the critical velocity. When this magnitude is equal to 1, then it would be exactly this. This would be a critical stream, I suppose. And a subcritical stream is when it's flowing slower than that magnitude and you can't communicate. So that's just the terminology that's used. And so what we'd like to be able to do, let me make this smaller, is we've already said that we index these behaviors in terms of maybe 3 dimensionless numbers. Euler number, which isn't so useful to us here. Reynolds number, maybe it's important. But for the other things that we also said that when we're talking about magnitudes of either friction factor or coefficient of drag or 1 over Manning coefficient, that we have these 2 behaviors: laminar regime, turbulent regime. And what we started off saying last time, always for open channel flows, we're probably in the turbulent regime. So from that point of view, maybe Reynolds number isn't going to be a particularly important number for us in classifying these flows. But what possibly is the magnitude of this number here, because this says something about how information is communicated from downstream to upstream. And so the easiest way to think about this is in terms of a critical Froude number, where there's a critical depth of flow and flowing at some flow rate. If it's flowing at still the same flow rate as this magnitude here, but now actually it's a different flow rate, but each one of these are the same flow rates, is it can be flowing either slowly and quite deep, or it can be flowing very quickly with a high velocity, same volumetric flow rate. So Q2 are the same in both of these cases, but by definition V2 here is less than V2 here. Then we get different behaviors, and this is the most efficient way for us to flow. We have much more energy loss within these systems that we deal with here. And so that's going to be our kind of mantra in dealing with free surface flows. Okay? So we've admitted the fact that we can have a flow depth that varies from upstream to downstream. And so by definition, that means that the velocity downstream in this particular case will be higher than the velocity upstream. We know that in reality the flow rate will be somehow distributed, so it's 0 velocity at the bottom, but we're going to ignore that and we're going to assume that the velocity is constant all the way down. We made the point before that actually it's no different from talking about flows within a pipe or flows around an object, is that we can still use Bernoulli's equation, which we have here. We know that Bernoulli's equation is written in terms of pressure, velocity, and elevation. Pressure is this magnitude here. Velocity is this magnitude here. And elevation is this magnitude here. That's a given. Downstream, we have the same. Pressure is this depth of flow. Elevation is this height here. And the velocity of flow is this height here. And the amount of dissipation of energy that we have in our system, if we write Bernoulli, it's constant as you go downstream. If there's a head loss, then we allow this. And so what we'd like to do is to take Bernoulli in exactly the same form as we've had before and to rearrange it in some terms that are perhaps more useful to us. And the terms that are useful to us are, first of all, that we will describe the change in this elevation, Z1 minus Z2, in terms of this slope of the bed, right? If we know the slope of the bed, then I think we could write that Z1 minus Z2 is equal to S0 times L. And the reason we can do that is that we could draw out this diagram here. This length here has to be Z1 minus Z2, right? This is Z2. Draw it across here. Then this height has to be Z1 minus Z2. We know that this length as we go downstream is some length L. And therefore, if you know the slope of this by definition, then it's just this relationship. And so these terms that we have in Bernoulli's equation, we can write in terms of the slope of the bed, just by using that as one of our defined variables. The pressure term we can write as being equal to this height here, right? So Y1 is going to be equal to the pressure measured at the base of this flow divided by unit weight. So I guess what I didn't say is that we're probably taking a streamline that goes along the base here, and we're writing for that streamline Bernoulli between upstream and downstream. And so this here is going to be, stop it. This here is going to be Y1. This is going to be Y2. We're going to take these two together and we're going to make them equal to this term here. And so now we have a couple of expressions left. We have the velocity head, upstream and downstream. Let's leave those alone for a moment. But we can define exactly what this head loss is here. This head loss is defined in terms of this energy line here. If we know the slope of this energy line and we define it as S sub f, then I guess we could write this behavior in terms of what's going to be. The analog to this expression would be S sub f is equal to the head loss divided by the length over which it occurs. Right? So if you accept this argument for this little triangle here as you go upstream, we can accept the behavior for this little triangle here as we go downstream. And so this we can define in terms of that. And so the reason for doing this is now that instead of defining it in terms of pressure heads and elevations, we now have converted into depths of flows and slopes of the bottom lines. And if we make those substitutions, we can rewrite Bernoulli's equation as this boxed equation here. If it turns out that the gradients of both the base of the bed and the energy line are the same, then we lose this last term, in which case the losses that occur along the flow, I guess it's basically saying that if this is the case, if these are equal to 0, then that means that this gradient of this bottom surface is exactly the same as the gradient of this top surface, but kind of backwards. And it's physically saying that the system is exactly balanced. The amount of energy that's lost in the system is exactly the same as the amount of energy that's put into the system by gravity, by it going downhill. And so that would be the case where we get rid of those. But anyway, so we can write it slightly differently. So what we haven't done is anything different than Bernoulli's equation right now. And so now what we'd like to do is try and generalize this not in terms of a flow velocity, which we know will be different in these systems, right? This velocity here, if the same flow rate occurs in each of these two systems, then this velocity here would be smaller than this velocity here. And you could think of the velocities being upstream, different locations. But rather than characterizing it in terms of the velocity, let's try and write Bernoulli's equation in terms of the volumetric flow rate. And so we're going to take this expression that we have, this, where, if you remember, embedded in this is the elevation terms, it's the slope of the bed, this is the head loss term, and this is pressure head and velocity head. And what we're going to do is we're going to think about flow across a channel. And this is the channel that we flow across. It has some depth of flow which we'll call Y. It has some volumetric flow rate which we'll call Q. And what we're going to do is we're going to define a flow per unit width of this channel, which we'll call the total flow rate divided by the width, right? So Q is the flow per unit width of the channel. If we know that the volumetric flow rate is just going to be the velocity multiplied by this full area, which I'm going to erase. Right? So Q is just equal to velocity times area. Velocity, the area, is the width of this channel multiplied by height, which is this. If we divide it through by the width of the channel, we get rid of these two terms here. And we have that the flow rate per unit width is just the velocity multiplied by the depth of flow, which I guess is the same as saying that also that the width of this flow is equal to 1 meter, the depth of this flow is equal to y, and so Q, if you like, is just equal to the area times the velocity, which is equal to 1 times y times velocity, which is exactly the same as this. So our reason for doing that now is that this expression here that we have written in terms of Bernoulli, if I wanted, how was it written before? Yeah, okay, this is how it's written. If we want to write it this way, in terms of this term that is upstream, which we'll call the energy which is downstream, which we could call E2, I suppose. The slope of the bed, the head loss within the system. So what we'd like to do is rearrange these in some way that is uniform. And so what we can do is we can take these two terms and we can modify it by doing what? We multiply this by y squared over y squared. And if we do that, then we see that this term velocity squared y squared is just going to be equal to lowercase q squared, which is this term here. And so now we have energy defined not in terms of velocities, which are different in each of these two cases, but in terms of flow rates per unit width, which were the same. So Q is the same in each of these cases. Q would also be the same in each of these two cases. So that's our reason for doing that. So now we have Bernoulli's equation, which is written in terms of this energy term, defined not as a velocity, but as a flow rate. And now what we can do is we can think of this energy term. If I help you a little bit, I can write y plus q squared over 2gy squared plus S0L is equal to y, this is upstream, this is downstream, this is squared, this isn't 2, but this is 1, right? This is q, I guess it's q squared over 2gy 2 plus SF times L. So this is Bernoulli's expression, nothing more. Pressure head, velocity head, Z1 minus Z2, elevation head, downstream pressure head, downstream velocity head, head loss. Those are the terms. Nothing other than Bernoulli's expression. We choose to call this term energy, which is this term here. And so what we could do is we could write this expression for energy just by rearranging it. We could multiply this expression by y squared. Which is this expression here. And if we do that, we see that we have a quadratic equation. We have a cubed term, a squared term, and a y to the 0 term. It's a cubic equation. So if we plot that equation for a constant value of the flow rate relative to the two variables of the depth of flow and the energy in the flow, and we plot it versus the depth of the flow and the energy in the flow, then we get an equation that has some squiggly line for any given flow rate. and the squiggly line will look like this. If we choose any particular energy, any particular value of energy that we want, then we know that it has three roots. In other words, it has three solutions to this equation. Two of the roots are real, and one of them is negative. A negative depth makes no sense, and so it's kind of an imaginary one if you think of it that way. So the point is that this behavior that we're looking at now has, for a flow at a given energy, these two flows we think have the same energy in them, but they configure themselves in two different ways. A deep, slow flow or a shallow, fast flow. They have the same amount of energy attached to them, and so you'd expect them to be on the same vertical line. And so if you think about what those flows are, you could imagine, if I just draw across here through this point here, this height here, and this height here, you could imagine, for instance, that that could be a flow that would look exactly like this. Upstream flow rate is something here. Here is a sluice, and here's the downstream flow height, which is being controlled by this sluice, and this is the bed of the water. And that's physically what this means. So all we've done is we've kind of taken Bernoulli's equation, we've written it upstream at point number 1, we've written it downstream at point number 2. The same flow rates occur through here by continuity. We've kind of enforced that. It conforms to this expression, which you can't see very well here, but you can imagine that this really is Bernoulli's equation. What this physically looks like is this curve where for a given flow rate, lowercase q, we have this curve here. If we have the same energy upstream as we do downstream, then we end up with these 2 points, and these 2 points merely represent two different levels in the system. And so this is a bass-ackwards from the system we had before, but it's really not very different from this. We have a flow depth upstream, a flow depth downstream. It's the opposite of what we just drew, but the same idea. And this would be a supercritical flow. It's faster than Froude number. It's a fast flow, but is not very deep. And we have a deeper slow flow, so this is a subcritical flow. And so that's really the definition of this diagram. But again, what we're doing is we're not doing anything different than using Bernoulli's equation to write things from upstream and downstream. All we're doing is we're casting it in a slightly different way in terms of things that we can physically measure in the field. We can measure the slope of a bed. We should be able to say something about the energy grade line and the loss of flow as we go along it. And those are two things that are more convenient for us to measure rather than anything else that we have in our system. Okay. So we'll talk a bit more about hydraulic jumps next time. I think we're right on time.